Yeah, indeed. This is, as he says, data resilience in an OpenQM system. This is an updated version of a presentation given some years ago to the International Spectrum Conference, but there's still plenty of good stuff in here. So the session is about data resilience. So that's protection against loss of data. We're not talking here about theft of data. That's a completely different topic, and we could do a talk sometime on encryption to deal with that one. But the question we should be asking ourselves if we're end users, or we should be asking our users if we're a reseller, is how long could your business survive without its data? And we need to think very carefully about that one, that even quite short outages can have detrimental effect on business. I have seen a customer who says a quarter of an hour without his system was enough that it would have a serious effect. So what we're going to see today then are things to do with data resilience, making sure we don't lose our data. And we'll start in a second by looking at causes of data loss, because unless we understand why we've lost the data, how we've lost the data, we can't really protect against such things. So we'll talk about causes of data loss. We'll talk about some simple steps to protect data, and some of those apply to all computer systems. Some are strictly QM, as we'll see. And the one that you've really all come along hoping for, will end the session with a section on data replication and talk about how that works, how we can use it in different manners inside our applications. So that's the plan for the session, and we're going to kick off, as I say, with causes of data loss. And for the purpose of this, I've divided my screen into 4 areas where we can put different causes that come along. So the first one is user error. And this is, as it says, by far the most common cause of data loss in computer systems. We accidentally delete the customer, or we overwrite one customer with another's data instead by accident. Or we give people access to command level and they start playing, basically. Oh, what does this delete command do? That sort of thing. Some years ago, I was involved in extensive research into data loss for a completely different product I was working on at the time. And we did a lot of analysis and discovered that user error is thousands of times ahead of everything else. So it's important that in our resilience strategy, we do as much as we can to protect against the user being an idiot along the way. My second category is software error. And this one might be the application itself. It might be the database package. We have to admit QM is bound to have bugs in it. We don't know what they are, but it's bound to have them. I'm a realist. It could be related software, because these days we don't tend to just buy a database and that's it. We go out and buy assorted other bits of software that will work with it. So it could be bugs in those. It could be, heaven forbid, bugs in the operating system underneath us. We've encountered those over the years. It could be bugs in the compilers that we use to build the product, or you use to build your application. Or it could be bugs in firmware and disk drives and controllers and all sorts of other places along the way. But those are all examples of software error that could lead to data resilience problems. Now, the top two sections on my my chart there, user error and software error, are both human in origin. Somebody made a mistake. We then move on to the ones that are not human in origin, and the next one that comes along is hardware failure. And this is typically the one we throw all our money at. We go on and we implement mirroring or redundant disk systems or replication or whatever to try and protect against hardware failure. And yet hardware failure these days is incredibly rare compared to the 2 above it on this chart. And then my final one is external issues. So fire, flood, earthquake, virus and ransomware we have to be very concerned about these days. Malicious actions there, and terrorism even getting in there as well. It's all things that could cause us loss of data. So throughout everything we talk about from this point onwards, we need to make sure that the topics we're covering actually are addressing all of these, and we haven't left a glaring hole in what we're protecting against. So we'll kick off with a nice easy one. Along the way, this is about data resilience. Remember, not losing data, that's what we do. But permissions are most commonly used by people to prevent unauthorized viewing of data. but there is no reason why we can't use them equally to protect against unauthorized overwriting or deletion of data. And because QM's file system is built around using the underlying operating system files to represent our data, all of the features the operating system provides in the way of group management and who can access what, who can do what, are all supported by QM. And we also honor completely the things like read-only status and so on. But in reality, we find that many people run their systems with no permission restrictions at all. I've seen many sites where they install whatever the software may be, QM included. They just do a quick chmod command 777, give everybody access to everything, usually with a sort of comment of, well, I'll sort it out later. But later may be too late along the way. QM will honor, as I say, read-only modes correctly. If you try to open a file and you've only got read-only access, it will open it, but read-only. So it's all fully honored. It doesn't fail the open along the way. So we can use that to protect our files in various ways there. And then when we want to get our permissions set right for the way the thing works, the QM documentation has a detailed list of permissions that are required on various system files, broken down as to the ones needed by administrators, the ones needed by users, the ones needed by developers, and so on. So simple one to kick us off there, permissions, and that obviously applies to a lot more than just QM, but there are some QM specific bits in there. And I make absolutely no excuse for including this next slide about effective backup policies, because over many years I delivered lots and lots of system administration courses and was staggered by the things people did with their backups along the way. So questions we should be asking, or our customers should be asking themselves about data loss and backups. I'll go very quickly through these ones because I don't want to dwell too much on this. But things we should think about, or they should think about, how often do you need to back up? Obviously, if we back up every 10 minutes, we can get the system back to a very close situation where we were, but we're not going to get much work done. Equally, if we only back up every month, then we've got a lot of work to restore if things go wrong. We had to fit our backup into our business routine. Unfortunately, a lot of sites these days don't have the luxury of an 8-hour downtime overnight to do backups and maintenance work. We have to fit it all in as we go along. And I have come across a customer who he said, well, because our system's quite big, we back up this area on Monday and this area on Tuesday and this bit over here on Wednesday, and he ends up with a completely unrestorable system at the end of it. Who performs the backups? Now that may seem a very, very silly question, who performs the backups? But the related to it is the what and who takes over if they're unavailable. And I have a tale of woe that I'm not going to tell here because it takes too long, about a major customer in the UK, not on QM, on a different product, who actually found that the person who's responsible for backups had left the company 18 months earlier and nobody knew that no one was doing backups. So horrendous along the way. Where do you keep them? I've seen people who keep their backups in a little rack on top of the machine. So the machine catches fire, there goes your backup. But the worst one I've ever seen was somebody who said, well, we leave the tape in for tomorrow night's backup. And they just went up and down the same one. How long do you keep them? In the UK, there is a legal requirement to keep financial data for 7 years. And I'm sure that applies similarly elsewhere. Maybe the time's different, but how long will you keep them? And there's a bullet that's not on this slide that says, once you get to that sort of distance into time, do you actually still have a hole the right shape to put the backup media in? Or has technology moved faster than your backups? And how quickly can you bring back your lost data? And what plans do you have to deal with a total system loss? I say, I've made no excuse for including that slide in this presentation because experience has shown teaching system admin courses just how many people get this desperately wrong. But back up in our OpenQM system, we can think specifically about how this all works in the QM world. So QM data files are represented by operating system directories. Therefore, we can use standard operating system backup tools to perform our backups. We don't have to have anything special. We don't have anything built into QM itself. But to make that work nicely, we can do standard tools. We can then go off to restore whole files or specific records should we need to. We can suspend and resume the system to ensure structural integrity. Now that's worth just a few seconds to talk about. The way the file system works, there will be links between various group blocks inside the file structures, and they are protected as we construct files, we update files, they're protected by various locking mechanisms. But if we come along to take a backup and we do our backup without suspending things, we could catch the system whilst it's in the middle of an update, changing a pointer somewhere, so that we end up with data that is actually lacks structural integrity. We can't restore it and get back a working file. So QM has a feature to suspend updates. You can say from the command line, you can say the operating system command line, you can say QM --suspend, and that will pause updates. And basically what happens is when a process comes along to try to do a write or a delete, it will simply stop and wait. And we then do our backup, or do enough to make our backup valid, maybe just a snapshot, something of that sort. And then we do QM-resume to kick everything off again. It all just picks up from where it was. Now that covers structural integrity. Data integrity is a different issue. And data integrity is about making sure that the data within the files is consistent. And the classic example of this one is moving money from one account to another. If we do our backup between the two steps there, either the money's in both accounts or it's in neither account. Obviously, we need to ensure that we do this at a time when everything is stable, and the solution to that is use of transactions in our programs, or a brief downtime if you can manage it, if you can survive that. The trouble with using transactions with existing applications is that retrofitting a transactional basis into existing applications is hard work. And it's hard work because the locking rules change. Locks get held for longer, and programs that have worked for years brilliantly suddenly start producing deadlocks. So we can use standard tools for that. What else can we do to try to control what's going on with our data? So QM uses security as an optional feature that limits the scope of damage in what users can do along the way. And it's something that when you install QM, it asks, do you want to enable this feature or not? And some of the things here are on all the time. Some of the things are controlled by whether you've enabled them or not. But it allows you to use various techniques. So we have enhanced security subroutines. I don't know whether security subroutines appear in all the different multi-value flavors or only some, but essentially what they do is they say a user can only execute some particular associated command when some conditions are met. And those conditions are applied by a user-written subroutine. And that could be things like you can only access this file or alter, amend this file between 9 and 5, or only members of certain user groups can amend files, and so forth. So in enhanced security subroutines, we've taken it a bit further from how they are in the other products I've seen them in, and extended them a little there to give more capabilities. We have account restrictions, which can allow or deny access to specific accounts. And if you enable these, what happens here is that you can control exactly where a user is allowed to go, including forcing him into a particular account as he enters QM to start with. And QMNet, which allows us to access data on other remote QM systems, has full user control as well. So the different users on the first QM system get different access rights as they connect across to a second QM system. Another thing that QM offers is something called Deferred Resize as a good way to make our file system more resilient. And essentially the issue here is that QM uses dynamic hash files that are automatically resizing themselves to respond to changes in the volume of data. So as the day goes on, as we write records or delete records from our files, things being moved around by the dynamic hashing algorithm. And that exposes us to the possibility, a slight increased risk of file corruption if we have a system failure. that we might actually just catch it at a moment when things are not in a terribly recoverable state, and we end up with a structural integrity problem in our files. So Deferred Resize says basically what I'm going to do is that part of the day, or maybe the whole day, I'm going to turn off the file restructuring mechanisms. So the dynamic file actually just begins to gather overflow as time goes on a little bit. Not vast amount usually, but a little bit of overflow gets generated. And then at a convenient moment, and ideally just after a system backup, we tell the system to catch up effectively with what it had held off doing. And this just closes the little window that some people are concerned about with dynamic files, that because things are moving around quite a lot, it is possible that you could catch it at a nasty moment and not have a consistent system. Deferred Resize gets us around that. And the cost of the catching up process is much faster than the complete resizing that would be involved if we had static files. Another thing called directory file update protection, which is very valuable. And this one is all about saying when I update a record in a directory file, the update could fail. And it could fail, for example, if there's insufficient disk space available for the update I'm trying to write. And this is a serious problem because when we start writing a modified record, we'll be overwriting the previous version. And it could be we've got halfway through writing the new version when we run out of disk space and the system then fails that write. Not only have we lost our new data, but we've lost the old data as well. There's a configuration parameter in QM called safedire. What this one does is it says when I write an update to a directory file, I write it to a temporary file first, temporary record alongside the original that I'm trying to change. And then having successfully written it, I delete the old version and rename the temporary version. And that gives us a much improved security against that sort of error. The performance impact is very small, so there's not a big issue introducing this. Now, obviously, in most systems these days, running out of disk space is pretty rare, but I have seen it recently. I've seen it on 2 or 3 customer sites in the past. It is something that does still happen occasionally. So those are some of the sort of miscellaneous bits and pieces, but the one that this section was all about introducing is the concept of data replication. And we're going to talk a little bit about how this one works in QM to bring us to the end of the topic. But this is a series of steps to get us there. So updates applied to replicated files are automatically copied to one or more target systems. So I can have a production server and my sales file, I can choose to copy changes I make there automatically to some backup system. And that might include using it for standby servers. So I've got a hot standby system. If my primary system fails, I can just switch my users across. We'll look at an example of that in a moment. I can use it to construct reporting servers. So where people are wanting to do the sort of intense what-if type reporting and doing masses of selects and sorting data and so on, we can move them to a second system. So our live system is not impacted by the work they're doing. We can use it for propagating updates to price lists and the like out on other systems. So it's not really bringing data in, but spreading data out in that case. And as we'll see, we can use this for merging data from separate sources into a single composite item. So how does it all work? I'll take you through a series of steps here. Let's imagine we have a sales system and we have a branch office for our company, busy selling whatever it may be that we deal with. The branch office can use replication to send a copy of everything they do to the regional office. So the region now gains a copy, a local copy of what is happening in the branch system. Now, not only does this give us a hot standby system, we can call back out to the branch from the region or the other way around if one system fails, but it also means we are gathering data together from potentially multiple branches. And if we do this one, if we're bringing in data from multiple branches into a single regional file, It might be that that regional file is just a single composite view of everything, all 3 branches in my example, or it might be that we keep them as 3 separate files at this stage on the regional site. So my branches are pushing data across to my regional office. And of course, I don't stop there. I've got a head office as well. The regional office can forward data onwards to the head office. Now, in QM terms, that step there is known as cascade replication, where we've taken one set of replicated data and passed it on to another destination along the way. And most of the other products that offer replication can't do this. So a change made in my branch office, any of those branch offices, will find its way to the region, and then from there it'll find its way down to the head office ultimately. But of course, I don't just have one region, I have many regions. We'll stick with 2 for this diagram, and I end up with this much more exciting looking diagram in which data collected from the outer layer, the branches, is navigating its way to the region and then onto the head office with the overall picture of everything. Now, if we're going to do this, and we're doing it, for example, for a sales file, then if we are merging the data together when we get to the region or the head office, then we'd have to make sure that the record IDs in the data files we're moving are unique. And typically we'd do that by including a branch number in the ID. So the problem of overwriting things from duplication of record IDs doesn't apply. The last step in this little process of describing replication is fairly subtle as far as the diagram goes, but fairly critical for real use of this in live applications. We make one last little change, which is that each of those arrows is now bidirectional. This is what we call symmetrical replication, where the data can go either way. If the branch up at the top left were to make a change, it would find its way to the region and onto the head office, as we had before, but it would also find its way out to the other 2 branches in that region. And from the head office, it would find itself into the region on the right-hand side of the diagram and onwards out to the branches. So a change made anywhere in this network of systems will find it to all of them. And that's really quite powerful, this idea of symmetrical replication. So how does replication work? Updates to the published files, the files you want to send out for other people, are written to a log file. And there's a log file for each subscriber system. So if I have a primary system, my production machine, that is the publisher that's making data available for others. And then I have other systems wanting to take copies of that. They're the subscribers. And on the publisher, there will be a log file for each subscriber system. And the upper copy of the updates is written to that log file. So I might be modifying many different data files on my primary system, but they're all going to the same subscriber. There is one subscriber log file recording all the updates. The subscriber system makes a connection back to the publisher and requests that it sends it a batch of updates. So it'll gather together out of the log file a collection of updates and fire them across the network, where the subscriber can then apply them to the files on that end of the system. And it then goes back and says, well, have you got any more? And some further data is sent across. And we do this around a loop, basically going around saying, send me some data, here it comes, send me some data, here it comes. And eventually it'll say, well, I haven't got any data left to do, you've got it all. And the system will then go into a sleep mechanism, and there's checkpointing applied to make sure that if at any point in there it all fails, we can get things back alive, typically from where that last sleep was. And all the network traffic involved in encryption in replication is encrypted for security purposes. Let's look at that as a diagram. In this diagram here, this is using replication for maintaining a standby system. I have my live system on the left and my standby system on the right. The blue disk is the actual real data file, and the green disk is the log file for replication. So at this stage, as I've got this one set up here, my live system, my users are connected to the live system. They'll be making changes to the blue file, and every change they make gets written into the log. And assuming everything's up and running, then the log file is being accessed, polled for by the standby system to move the data across the network to the standby box. And because of where we're heading with this, I've actually said, well, let's also have in there a log file to go onwards, as we will see in a moment. Now, what happens, of course, is I have a disaster, my live system dies. I simply move my users to the standby system, and they just simply log in again, basically, to get there. And they will have all the data that was on the live system up to, well, maybe the last couple of seconds and hadn't gone across, but the bulk of the data would be there. The users now carry on. And we had a failure of this sort with a system here some time ago, where we had a system that was providing the OpenQM website those days, and it had a standby system mirroring it. And we had a power supply failure on the live system, moving the users across. It's a web application, so they're all transient connections. Moving the users across required nothing more than changing the IP address in the router. Job done. Everything just moved across. So, okay, so we now got our users on the standby system. We can repair the live system, put the fire out or whatever it might be that's going on there. We can repair that one, and then we're ready to get people back. Now, there's no urgency to this because the two systems are in step with each other, hopefully. But what we would end up doing is putting the systems back together now by making sure that the standby system fires data back to the live system. Now, because of how symmetrical replication works, it never sends data back to where it came from. So it will take the updates across that are needed, but anything that is irrelevant to this particular move will sit in the log file to go somewhere else. And then our users can reconnect. Now, configuring replication in QM is remarkably easy. Replication is an add-on optional component. So we have to decide whether we want this or not, and if we do, then we get that added to our license. It's licensed on the publisher system only. So if you have one publisher sending data to 25 subscribers, that's still only the one system actually requires licensing of the replication. Publishers come free, subscribers come free. If the primary system is part of a dual standby license, and that standby license has replication on the primary, it is automatically also on the standby, because by definition here we'd be wanting to use symmetrical replication going both ways, so the system provides that as standard. Now, configuring it is straightforward. On the publisher system, we have to set 4 configuration parameters. RepLDir gives us the directory name for the location where we're keeping our replication log files. RepLMax is the maximum number of subscriber systems that can connect simultaneously, and that's needed just for sizing data structures in memory. RepLPort is the port we listen on for the QM RPL, the replication processor along the way, and that defaults to port 4244, following the trend of QM's port numbering. And RepLSize is the size of a log file when we say, oh, enough is enough, let's start a new log file to take the next burst of data. And so what we end up with is a series of log files of this limited size, and they will get automatically deleted as the system applies the updates to the subscriber systems. For the subscriber side, we just have to set a couple of configuration parameters. We need to set the net files parameter to mode 2 to allow QM net access. That's actually only needed while you're configuring replication. Once it's configured, it's no longer needed, but it is normal to leave it there. And there's a configuration parameter called RepLServer, which sets the name of the subscriber system. And this is the name that you'll use on the publisher when connecting to it. It's not necessarily the same as the computer's real network name. It is something that's purely internal to QM. So that's got the system configured to do replication. How do we then say, well, particular files that I want to replicate? The process of publishing things is very easy. We have a command called publish. And you simply say publish, you tell the file name that you want to publish, and then one or more destinations, which are put in as server name, account name, file name. And this one will publish that name file to one or more targets to do that. From having done that republish command, from that point forwards, everything that you do to that file gets export across automatically. Now, obviously, you don't want to publish just one file. You probably want to publish hundreds of files in all this. And so to make life easy, there's a command called publish account, and that one just takes a server and account name on the back, and then comes up with an interactive screen in which you basically run a pick list of which files you want to replicate and which ones you don't. So publishing replication is extremely easy. I have, in fact, today just been using this for something, testing here, and it took probably no more than a couple of minutes to configure it. To subscribe to the updates, we're carefully publishing and they're not going anywhere yet. We need to do one last step here, which is the subscribe command. And the subscribe command is done on the subscriber system to say, I want to connect back to the named server and I want to bring updates across to apply to the files locally. Now, the subscribe command starts a phantom process that will manage the process of polling for replicated data. It's normally executed as part of a system startup script so that it happens automatically. And you can configure on the command line as an option, you can configure the poll interval, how frequently it asks for updates. And when you do that, and it goes to sleep because there are no further updates waiting, the default period is 5 seconds. And that means on average, your publisher system is running sort of 2.5 seconds behind the live system. And the authentication details, the username and password, can be encrypted on the command line. There's a tool to do that, so we're not giving away the keys to the world. And then the last thing we're going to talk about here is account replication. And this one says, well, it's all very nice that I can get my data to be replicated across. Every change I make to this file gets mimicked across to the other system. It would be nice if we could actually get other things done automatically. And this one says, well, selected commands executed on the publisher can automatically be executed on the subscriber too. So as well as passing the data across as and when, several commands take part in this. Create and delete file. Create, build and delete index, catalog program, adding and removing distributed file components, or setting queue pointers. You can configure the system so that any or all of those is replicated across to the target system. And it means that if I come along and I need to add a new file, for example, to my application, I can do the create file on the live system. The file is automatically constructed on the target system. I can go on to then build indices in the same way and so forth. I don't have to go over there and do all this work separately on the second system. Now that's it as far as this core presentation goes. It's question time from there on. So we've rattled through a number of things to do with resilience. They say what we're dealing with there is protection against loss of data, not theft of data.
Well, I think that's all we got. So thank you, ladies and gentlemen, for joining us. Martin, great job. And thank you for putting this together. We appreciate it.
You're welcome.
All right, everyone. Be well. Take care.